Hey there, welcome to this video on digital topography and elevation data sets. So digital topography and the display and interpretation of it is a huge tool in earth science research. And if you need an example, here's a digital elevation model that's been turned into a shaded relief image of New England. So this is the Champlain Valley, Lake Champlain here, Montreal up here, the Adirondacks here, and the White Mountains over here. And just looking at this beautiful image, you can interpret so much of the geology. Here we have the Monteregion Hills, a series of igneous plutons that have intruded 100 million years ago and have been difficult to erode. Here we have fracturing in the Adirondacks, telling us the story of how the Adirondacks were formed and exhumed. Here we have the north-south strike of the Green Mountains, right? This elongate north-south fabric showing us that the tectonic belts of the Green Mountains were emplaced along north-south striking thrust faults in an east-to-west compression direction. So there's so much we can learn from digital topography, and it's just endlessly fascinating. So what is digital topography? Well, we'll often use the term digital elevation model, or DEM. Sometimes you'll also see digital terrain model, DTM. And it sounds fancy, but it's not. It's just a grid or a raster of elevation values. So instead of an image where each pixel represents the brightness in the image, each pixel in a DEM represents elevation. It's just as simple as that. So this pixel is 664 meters height, 714 meters height, and so on. And we usually do two main things with a DEM. We can either visualize it, like I just showed you, or we can use it for calculations of things like slope, or identifying flow paths of rivers, or identifying lakes, things like that. So in this video, I'm actually going to focus mostly just on giving you an overview of different elevation data sets that are at your disposal. And then in future videos, we'll talk about how to use them. So if you're living in the United States, one of the most important data sets for you is the National Elevation Data Set, the NED. This is available typically on the National Map server that's maintained by the USGS. Covers the entire US at various resolutions, 30 meter, 10 meter, and 3.3 meter. Pixel sizes are the main ones. Notice you'll often see these expressed as 1 arc second is 30 meters, 1/3 arc second is roughly 10 meters, and 1/9 arc second is roughly 3.3. So what does that mean? What's an arc second? It's a reference to a radial latitude and longitude grid, as in degrees, minutes, seconds. So a 1 second DEM, the pixel size is equal to 1 second at the equator, as in degrees, minutes, seconds. So we can go back and forth between meters and arc seconds. And importantly, this NED data set is compiled from different sources. The coarser 30 meter and 10 meters are either derived from contour maps or from the SRTM data, and the finer grain stuff, the 3.3 meter, is usually derived from LiDAR. And you can see the differences here, right? Here's the 30 meter data set where you can't see some of the finest features. And then as we come into a 10 meter resolution, we can start to see the river channel really clearly, some older channels here. And then as you come to the 3.3 meter, wow, you can see all the detail of these abandoned channels and lots of other things, maybe a fence line right here. So high resolution topographic data, meaning smaller pixels, has a lot of information. Okay, so another important data set is the Shuttle Radar Topography Mission, or the SRTM. This was a huge deal. This was the first globally consistent elevation data set collected in the year 2000. So prior to this, each country might have maintained its own classified information about elevation of other countries, or maybe you could find some old Russian topo maps in the Berkeley Library. But then this mission happened and actually collected a unified, consistent elevation data set for the whole world. And the way it did so, it was collected from a space shuttle that orbited Earth for about 2 weeks. And it had 2 radar antennas, one in the cargo bay and one hanging out on a 200-foot long antenna. And using these 2 radar antennas, it was able to do what's called synthetic aperture radar and generate pretty high resolution and accurate elevation information for Earth's surface. So this is available now in 30 meter pixels, or 1 arc second, for the whole world. As of about 2015, that was released. But you can also find it, sometimes it's important to use this G-Topo30 data set, which is resampled into 1 kilometer pixels. So if you're trying to display the entire western United States and you don't want to have a lot of large files, you may want to pick to use the 1 kilometer resolution, the G-Topo30. The horizontal accuracy is about less than 20 meters, and the vertical accuracy is less than plus or minus 16 meters. So that's pretty accurate. And one great thing about the SRTM mission was that the long wavelength radar that was used in the mission penetrates the tree canopy. So even in like jungle places, the rainforest, or thick canopies, it actually is a pretty accurate estimate of ground surface elevation because the radar bounced off the ground in many places. Okay, so a third type of elevation data that's also pretty useful is called the ASTER GDEM, and it's now on version 3. This is another global elevation data set. It has a 30-meter resolution similar to the SRTM, and it was actually creation of this ASTER data set that I think helped promote release of the SRTM global set. This is different, though. This is created by optical image photogrammetry. Essentially, the ASTER camera was able to look in multiple directions. So as it was flying along its track in this direction, it would first collect an image directly below it at nadir. Then it would fly along for about a second, and then it would look back at an angle of 27.6 degrees and take a photo of the exact same ground footprint. And so essentially this is a stereo pair of images from which elevation can be computed quite readily. So this has a horizontal resolution of about plus or minus 71 meters, not quite as good as SRTM, vertical accuracy of about plus or minus 17 meters at the 2 sigma level, so it's about the same as SRTM. One thing traditionally with the ASTER GDEM is because it is created by optical pixel correlation, it can be somewhat inaccurate in places where it's hard to correlate pixels. In other words, like over snow, for example, or over the Sahara Desert where it's all sand and everything looks the same, or perhaps over a very dense canopy like the rainforest. So the ASTER GDEM generally isn't quite as high quality as the SRTM dataset. And so another type of data that's always worth considering is airborne LiDAR data. And we're going to talk more about this later in the class, but airborne LiDAR data is collected by pulsing a laser from a plane. So essentially the plane flies in a grid across some very small area, like a town or a county, and it pulses laser points off the ground. The two-way travel time of the laser pulse gives you the distance to the ground and the elevation of the Earth's surface. Because the density of the laser shots is so high, we can generate digital elevation models anywhere from a meter pixel resolution even down to much less than that, a quarter meter resolution in some cases. This is typically flown with leaf off, so often this is going to be a bare Earth digital terrain model, which is very helpful. But of course, the spatial footprint is limited. So these LiDAR data sets are huge. The files are huge. They tend to occur in small postage stamps, and you need to often mosaic them together. But really, a LiDAR revolution is sweeping the United States, and there's a huge amount of data available. So here's an example of the type of high-resolution imagery you can get with LiDAR data. You can see roads coming through here. This is a quarry right here. You can see the footprints of houses that have been removed by a cleaning algorithm, but it very clearly picks out houses, very clearly picks out details of all these river channels, so it's extremely high resolution. And as I was saying, a revolution is sweeping the U.S. We have each day, each year, many new LiDAR data sets, to the point that we are, slowly approaching full LiDAR coverage for the USA. So this can be a good choice if you want very high resolution data for a smaller area, but it's not a good choice for projects that might cover an entire state or a region. You can look for LiDAR data all over the place. Open Topography is a great place to look, and also a lot of state and local distributors. In Vermont, VCGI is very important. Okay, so to wrap up here, a couple other elevation data sets that are worth mentioning. The ALOS radar-derived DEM. This is another 30-meter resolution with global coverage. TerraSarX is the satellite, and the Terra DEM is derived from it. This is a 12-meter resolution global coverage. However, it is proprietary, so you have to request the data. It takes a couple months to get it if your request is approved, but it's a pretty high-resolution data set, and it's often the best you can get for remote places. So we did a project in the Sahara Desert where there's no good topo maps of any kind, and we were able to get this 12-meter resolution DEM, and it was quite helpful for that area. Then finally, the Hydrosheds global DEM. Basically what these folks did is they took the SRTM, they did hydrologic conditioning on it to make sure all the rivers flowed in the right directions and the watershed boundaries were correct, and the lakes were not causing trouble. So this is great, especially for kind of regional scale hydrologic analysis. I recommend the Hydrosheds global DEM. They also have a lot of derived hydrologic products like flow lines and things like that. Okay, and then to really close out, a word on the vertical units and the formats of digital topography data. So obviously the elevation is going to be in some unit. Usually that is meters. Occasionally that'll be feet in the good old USA. You can always figure it out by just using common sense or looking in the metadata. Low resolution elevation data, so like the GTopo 30, will often come in integer format where there's no decimals. Elevation is rounded to the nearest integer. But high resolution data like LiDAR usually will come in a 32-bit floating point. Reason for that is that larger format can record the decimals. And in LiDAR data, that's very important, right? LiDAR can tell the difference between 68.3 and 68.4 meters quite readily. And so that it's important to keep that information in the file. So we use a 32-bit floating point for that. Common file formats, you'll see lots of different formats. GeoTIFF, if you can get it, is the best, I think. But also you'll find elevation data in ASCII format. It's basically a text file. erdos.img, bandinterleaved.bil, sometimes Esri grid, sometimes .hgt. So often you have to do a little research on how to import your elevation data into your GIS software, although ArcMap is quite handy. And of course, often you'll find yourself downloading multiple tiles at a time, and you'll need to be mosaicked or merged. And as you do that, as you merge them, take care to preserve the file format. One common mistake is to accidentally, as you're mosaicing, convert your data from floating point into integer format, for example. Well, I hope this is helpful, and enjoy your digital topography.